28. Define mutual inductance and write its SI unit. Second, B part. Two circular loops, one of small radius r and other of large radius capital R, such that capital R is very large than small r, are placed coaxially with centers coinciding. Obtain the mutual inductance of the arrangement. 28a. Mutual inductance. We know that phi equals to mi. The flux, so if I equals to 1 ampere, then phi equals to m. So we can define this way. There are two definitions. We can define it in two ways. One is the flux produced in the second coil. The flux produced in the second coil when 1 ampere current is passed through the first coil. Second way, it is E equals to minus d phi by dt, that is minus m di by dt. If we just neglect this negative sign, this for the sake of definition, it is only giving the direction. So if di by dt is equal to 1 ampere per second, then E equals to m. So this way we can define mutual inductance of the two coils is the induced EMF produced in the second coil when the rate of change of current in the first coil is unity, or you can say 1 ampere per second, and its unit is Henry. (28b). There is a small loop of radius small r and a large loop of radius capital R. Let us consider the current passing through this loop is I. Therefore, here the R is very large than small r. Therefore, the magnetic induction produced at the location of this small loop due to the bigger loop will be B equals to mu naught I upon 2R. The flux produced at the loop across the or within this smaller loop will be equals to B into area of the small loop, that will be equal to mu naught I upon 2R into pi small r square. Also, mutual inductance between the two coils is always equals to phi upon I. That means this is equal to mu naught pi r square upon 2r. So the mutual inductance of these two loops will be mu naught pi r square upon 2r. 20th OR part. Two long straight parallel current carrying conductors are kept a distance apart in air. The direction of the current in both the conductors is same. Find the magnitude of force per unit length and direction of the force between them. Hence, define 1 ampere. So let us consider here two conductors. As stated, they are separated by a small distance A. So this is the first conductor and I'll call it second conductor. The current passing through the first conductor is I1 and passing through this second conductor is I2. Let us consider a small length of this conductor as L2. So first of all, we'll try to find out the magnetic induction B1 due to the first conductor at the location of the L2, that is mu naught I1 upon 2 pi r, that is A. Here it is distance A. Now the force on the second conductor, that on L1 L2 length, force on second conductor due to the first conductor will be equals to I L and B. So I is here I2, length is L2, and B is here B1. So this value will come I2 L2 mu naught I1 upon 2 pi A. So this F21 equals to mu naught I1 I2 L2 upon 2 pi A. So this force per unit length, that is upon L2, will become mu naught I1 I2 upon 2 pi A. In the similar fashion, we can just consider here current flowing through this and a small length L1 here. So the magnetic induction B2 at the location of L1 due to the second conductor will be equals to mu naught I2 upon 2 pi A. So the force on the first conductor due to the second conductor, that is the force on 1 due to 2, will be equals to the current, length and ILB. So I this time will be I1, L will be L1 and B will be the due to second conductor. So that is equals to F12 equals to I1 L1 and this is mu naught I2 upon 2 pi A. So force on 1 due to 2 per unit length L1 will be equals to mu naught I1 I2 upon 2 pi A. So here we see that F12 upon L2 is same as upon L1 is same as F21 upon L2. So this force is equal, and where will be the direction? The direction will be obtained by Fleming's left hand rule. So first of all, we will use the right hand palm rule or right hand grip rule. The magnetic field induction at the location of the second due to the first will be inward, that is, so they will get the inside, or you can say palm rule. You just put the palm over here and this direction of the thumb in this way. So the palm is inward. So this is the inward. And gripping this, you have to grip it, then the magnetic force will be passing through the inward. And due to this, this will be outward because these fingers will come out, or you can say the palm will be outside. So this way, this is outward. Now Fleming left hand rule. If this is the magnetic field and this is the direction of the current, so this is the magnetic field inward, this is the direction of the current, so the force is in this direction. So this force is force on 2 due to 1, that is this way. Similarly here the magnetic field is this direction and current is this side, so the magnetic force will be in this direction. So this will be force on 1 due to 2. So they are equal. F12 is equals to F21 but in opposite direction per unit length. So they are equal and opposite. So direction is inward, and attractive force is there. Now how to define 1 ampere? So if we take this expression or this expression, it's one and the same thing. So here we have F upon L is equals to mu naught I1 I2 upon 2 pi A. To define 1 ampere current, we can take F upon L is equal to mu naught I1 I2 upon 2 pi A, And if I1 is equal to I2 is equal to 1 ampere and A equals to 1 meter, then this force per unit length will be equals to mu naught upon 2 pi, and mu naught is 4 pi into 10 to the power minus 7 divided by 2 pi. So that comes to be 2 into 10 to the power minus 7 Newton per meter. So that means when two conductors, long conductors, are placed in vacuum at a separation of 1 meter and they are carrying each are carrying equal currents, if the force of the mutual force between these two conductors per unit length is 2 into 10 to the power minus 7 Newton per meter, then we can say that the current flowing through each of the conductor will be 1 ampere. So this way you can define it.